I'm Ricardo Mendes. We're going to be talking about flexibility to immutability. And we're still getting people, so let's get them a bit. So, first of all, a quick warning. I'm going to be talking about opinions and giving anecdotal evidence. It would be really nice if I could stand here and present some sort of ironclad, demonstrable argument about why you should do this, hopefully based on multiple teams with a control group of some sort, but we don't really have that. All we have is our own experience, and I'm going to be talking about my own. And since it contains opinions, this will not be a masterclass. So if you disagree with anything, just make a note of it. We can discuss about it near the end. I'm trying to leave about 5 minutes or thereabouts for questions, so we can get a discussion rolling near the end. Just come in. So what we'll talk about. First, I'm going to give a quick background on immutable data and functional programming. I'm going to be talking about advantages and trade-offs, effectively why bother doing this if it's different from what you're used to. Then I'm going to give you 4 simple guidelines that you can do it to put this in practice in an object-oriented programming language. Mostly so that you don't, if you want to try data immutability, you don't have to pay the extra cost of moving to a different language and the learning curve that comes with that. So it's always a bit difficult to prepare a talk without knowing who the audience is, and it's maybe difficult for you guys to realize where I'm coming from. So let's first get an idea of audience composition. As I mentioned, I'm a software engineer, or as you can imagine, I'm a software engineer. I run Emergent. I work mostly with data-oriented projects at media agencies, healthcare companies, things that have to do with information management, and financial companies, which probably helps give you an idea of why I consider state bugs that big of a problem. I run project-specific distributed development teams, and I've been doing software development professionally for over 20 years and hacking around for longer. So this is not my first paradigm. This is not the first thing that I've encountered. I've been all around the block, even deployed a COBOL application once, so that gives you a bit of an idea. Now, to get an idea about you, anyone's here working without garbage collection, like somebody doing C++ or C development? Okay, so if so, I'm not sure how useful this is going to be for you.
Because with and without.
Oh, okay, perfect. Because to really get some advantage out of data immutability without having to build a whole bunch of rigging yourself, you're going to need some form of garbage collection, making sure that you can sweep away the stuff that you're not using. Now, who's already working on a purely functional or a mostly functional programming language like Clojure, Scala, F#? Okay, one guy, cool. That's easy, and the one that I knew. Now, what are the rest of you working on? Let's say Python. Okay, 1, 2, Ruby, Java, C#. Perfect. that actually makes my job easier. Now, those of you who are using already, who of you are using immutable data somewhere already? Cool. Now, let's talk about my path here first. I actually started doing functional programming just as a way to learn something new, mostly because it was different from what I was working on. It promised I could learn a new way of thinking. And learning something new, particularly new paradigms, always gives you a new perspective on things, even on things that might not be directly related to it. And something unexpected that happened to me after doing functional programming for a while, as I was mentioning earlier, having to come back to a functional code base some months after, was that it made me realize that it had the unexpected benefit that code was easier to refactor. Code that was purely functional, which did not mutate data at all, was easier to change for me after. And let me give you a couple examples that are going to seem trivial, but I'll go into the possible ramifications of this. Suppose you have this simple C# code. I'm not talking about refactoring just as adding parameters. We have this calculate force function. Looks pretty straightforward, right? Now, what if we don't need this result value anymore? Can we just delete the code? Can we assume that it's not going to have any implications on the concept? we really can't. We need to first know that we make sure what's going on inside that function. For instance, is it caching any value? Maybe it's storing a last time force calculation if the force calculation is very elaborate. Maybe it is setting a timestamp somewhere. Maybe it's causing a side effect on the object itself that is not immediately evident from this simple call. So we can't just go around and remove it without first knowing exactly what's going on inside it. Now, I wrote this code. I know that this function is relatively simple and just goes to a list of vectors and return a value, but that's because I wrote it. You reading it from the outside don't really know what's going on in there and have to take it on faith, which is a problem that I found with mutable data. When you're looking from the outside at a method that handles mutable data, you have to take the implementation on faith. And I hadn't realized before how much of the code we handle ends up with us doing this. And frankly, if you've never in your career run into a surprise like this, where you just remove a function and it turns out that somebody inside was causing some side effect that the rest of the application was hoping on, you'd have to be really, really lucky. And it doesn't have to be code written by a novice programmer. Sometimes even experienced people just put it in as a hack quickly and then we forget about it. Now, how about this other case? Fairly simple to read, right? It's just, it initializes an array randomizer with a particular type. It receives an image list. Then you can use that instance to return a random subset using the Fisher-Yates randomization algorithm. Pretty straightforward, what could possibly go wrong? Well, there's two problems here right away. The first is that we're returning a list. This list of items, anybody who can get a hold of this, anybody that we can pass this list to, can modify it, can change the elements that are contained in it as well, because we're just returning a list of references. The second one is that we are initializing this randomizer from an image list. And notice that on this very straightforward piece of code, we don't really know where this image list is coming from. We don't know who else is holding it. We don't know who else has a pointer to the items that are inside it. We keep an instance of the array randomizer because it pre-calculates some information. But once we have initialized the array randomizer, it really has no way of knowing if the data that it was initialized from has changed or not. And this situation where we run into an object that might be relatively long-lived, and by long-lived here I don't mean hours, we could be even talking half a second, can trigger state side effects when we have objects that are referenced in multiple places. So this brings me to why bother with immutable data at all. The first is that there is no frictionless movement, actually. And the more moving parts that we have in our system, the more things that are referencing a single piece of data, like in that case of that list that we're passing, the more friction that we're going to get. So we want to remove the movable pieces. The second is that I found that when dealing about immutable data, I stopped thinking about operations and started thinking about results. The difference might seem subtle, but the key thing is that I didn't really care what was going on inside a function or inside a method call. I only care about what this thing sent back. As long as the result was consistent, I did not care about the implementation one bit. I did not have to care about what it might be changing because it couldn't be changing anything. And this might seem like a small thing, but functions that act on the same dataset become idempotent, which means that you can memoize and cache the value. This has performance implications when you're dealing with very large datasets. Now, of course, I'm pretty much saying be more functional. So if you're already sold on the idea of being more functional, well, and actively doing it, by all means, stick around and you can help me convert those who aren't. Now, this is something that I was making earlier on one of the open spaces, which is that immutability tends to get conflated with statelessness. They're not actually the same thing, and I think it is the same way. It is the wrong way of going about it. Think about yourselves, for instance. You have a state, right? Your state is your worldview. You have a preferred programming language. You have a preferred platform. You have likes and dislikes. chances are that whatever likes and dislikes or preferences you have now are not the same that you had 10 years ago. But you still remember your old state. You didn't just, as soon as you have the memory of a goldfish, you didn't just have a single space in your mind where you completely overwrote your previous knowledge. So when your personal state changes, you don't discard the knowledge that you used to have before. And this is precisely the sort of thing that we're aiming in our systems, where we can carry our state forward through time without losing information or without invalidating any processes that might be working based on the old state. So, since I said we're going to be following a more functional approach, let's talk about what that means. And I'm not going to bore you with the Wikipedia definition of functional programming and make you read a whole bunch of text. But we'll point out what we're aiming for here, which is, first of all, we have functions which have many inputs and one single output. The single output may be a composite value, like it may be a tuple, or it may be a struct, or it may be a dictionary or a list, but it has a single output. There's no refs to the method, there's no outs, there's nothing being changed, which is why we're dealing with values here. Values are immutable. We don't change them. When we call a method on them, they don't change themselves. Nobody changes anything, period. And this is because pure functions do not trigger any state side effects on the inputs, on the outputs, on anywhere else. Bear in mind that these three things tells us that it's not just about the language. Functional is about learning new semantics. This is a point that I made on the talk that I gave on the Bucharest functional programming meetup a few months ago. It doesn't necessarily mean that you need to learn a new syntax. It just means that you need to learn new concepts and to get used to work in a different manner. Functional is just about semantics. Languages help. F# Clojure are going to help you by enforcing mutable data, but you don't necessarily need to go that way. In fact, I really liked one line that Constantin Dumitrescu had at the last Bucharest FP meetup, where he said that the pure functions are the most boring thing in the universe. And that's exactly right. That's what they should be. I mean, we should be excited about working with boring things. We want our basic tools to be boring and predictable, not surprising and exciting, and we have no idea what they're going to deliver tomorrow. It's what you create with them that should be exciting. So, show of hands again. Who were C# and Java users here or working with on the platform? Perfect. Now, let's talk about strings. Do you have a problem understanding how strings work? Does anyone think here that strings are exciting? Good. I was really worried that somebody was going to say yes. Are you worried that the string is going to change from under you? Say that if you take a string and you pass it to a function, it's going to come back with, I don't know, trimmed, or it's going to come back all caps or something of the sort? Are you concerned that if you use it as a key in a dictionary, you're not going to be able to find the result value after? The reason and you never had to check the string implementation to validate any of these concerns, right? You just know it for a fact. And the reason why this is that way is because strings are boring, reliable, immutable data items. Any operation that you're going to do on a string with Java or C# is going to return a new item with the change applied. It's not going to change the item that you passed to it. So of course, what I'm saying is that you can do this in C# or Java. You need to move to a crazy functional programming language, no matter how cool it is. But even though we can, we don't, right? Most of the time, we could do this on C# or Java, but we just don't. We have a void do something to object method that returns nothing but affects a whole bunch of changes. We have lists with in place add and remove that just modify the collection itself. And we have ref and out parameters and functions. And then we pass these objects to other objects that hold this and that may, God forbid, call add remove on the list themselves. And at the end of the day, we just don't really know exactly who's modifying what. And the key thing is that every day we have to deal with unknowns in any code base. It doesn't really matter the language or the person's level of expertise. So consider this code, for instance. This is some Clojure code. Anybody can here can read closure comfortably? Okay, 3 people. That's like the same number of people who are using Drooly. So who thinks that this looks like unintelligible gibberish? No, perfect. Now, suppose that after looking at it for a while, or I just come in and tell you that this takes a bunch of data on this thing here, which is a hash map actually. It's actually a dictionary, and calls accumulate site times to operate on it. Now, if we're dealing with mutable data, there's 2 ways, well actually in any case, there's 2 ways that we can go at it to figure out how this operates. The first one is that we can poke the function. Tests are one way of poking the function. You know, we poke it, we see what it returns, but if you were dealing with a purely functional approach, we'd only need to see at what it sends back. If we're dealing with a mutable approach, then we need to look at what it sends back. We need to look at any changes it may have done on the parameter that we sent, and we may need to look at any changes from the object in which we're coded. Now we suddenly have 3 times as much work. And the second one is that we could just read the code. You know, this could be a relatively straightforward function, but for all you know, it's methods all the way down. And that is the only way that we would have in a mutable language to be entirely sure of what is going on inside it. I mean, we don't really know right now how accumulate site times is doing its thing, but we have the issue that being fully acquainted with the code is the only option to really know what's going on when we're dealing with mutable data. And I think we can all agree that option 2 here is significantly more time consuming. Even if we wanted to go this route, we will need 2 requirements. First, we need to have access to every source involved in the code. And second, we need to have the time available to go through it. Because I'm sure if there's something that you guys have encountered, is that if there's something that we have a lot of in projects, it's available time, right? So the thing here is that we have unknowns everywhere. And the larger the team, the more unknowns there are going to be. For instance, maybe not everybody on your team is going to understand the subtleties of the language. As we were talking earlier, there are cases about when you're doing with method overriders, differences between override and hidden. If you're using C#, do they fully grok link and it will link you and you wrote some of your functions in link you, or are they cargo coding part of the implementation? Are they, God forbid, a bit fussy on the difference on ref versus out? And the second one is that not everybody on your team is going to understand the subtleties of your code base. Do they not realize when reading a particular piece of code that something is a struct, and in this particular case is something that's being passed by value and not reference? Do they see a property called object.someValue and not realize that instead of just being a public properties getter and setter methods that may be triggering side effects? Do they see a method called object.getValue and not realize that somebody broke single responsibility principle inside it? And of course we could say, but single responsibility principle, who's ever going to break that? But the thing is that even when the best intentions, even with the best design, I think that we can agree that drawing single responsibility lines is really difficult when we have cross-cutting concerns. At some point, it's going to involve a certain amount of you making a call and deciding that this is single responsibility enough. And at this point is where assumptions and unknowns come in. Now, suppose that no method does more than one thing. Suppose that we can apply this thing religiously so that it's trivial to know what a method does at a single glance. You're going to end up with a whole bunch of them. Eventually, you're going to encapsulate your herd of methods, because the applications that we do are not that simple. If they were, pretty much any approach would do, procedural, functional, object-oriented. What we're trying here is to deal with complexity. And the thing with encapsulation is that while it reduces mental clutter, it also obscures. And when we obscure things, by definition, we're going to miss things. On our effort to make the code base more readable, we are actually decreasing the comprehensibility, which is what we should be focusing on, because readable is just a matter of habit, and comprehensibility is what we should be aiming for. Readability is only a small factor. Why I'm saying this is because these functional patterns may seem less readable at first, but that is just because you're used to the older way of doing things. If your code as a whole is more comprehensible, that is a massive win in the long term, because as I'm sure you have encountered, the code is read more than it is written. So let's talk about how to do functional programming in an object-oriented language, and I'm going to go over 4 very simple principles, so this is not going to take a lot of time. I'm going to focus most of my examples on C# and Java, since .NET and Java are the platforms that I have the most recent experience with, but I'm sure that you can take this and translate them elsewhere. The first is that in .NET, structs can act as a gateway drug. It's really nice that the language by default enforces passing them as reference, not value, but I'm curious, who here uses more structs than classes in their daily work? Right? You. Okay, one person. That's a new. Classes have their advantages. So we need to do things like, well, structs help, we need to do things in a way that we can use them with classes. Which is where the second principle comes in, which is very straightforward. Don't mutate your objects. Make sure they don't mutate themselves. And that nobody writes methods that mutate them. This is just an issue of discipline. So for instance, if you have a vector class that stores a particular vector and you need to normalize this vector, then don't do a method that's vector.normalize. Have a normalized property which returns a new instance instead of changing the values for the vector in place. If you have an employee and you need to change the salary, don't just have a property for employee.salary that anybody can come in and modify from anywhere. Have a method that receives a salary change and returns a new instance with the changed salary. This also is going to have the side effect that then you're going to be able to chain your codes fluently. And if this is starting to look a bit like the builder programming pattern, you have the right idea. That's kind of what we're aiming for here. The third is that we have to bear in mind that there's no problem that cannot be solved by an extra layer of indirection, other than too many layers of indirection, and this is another case. While I'm taking writing for the interface, not the implementation one further, I would like to suggest that you need to write for enumerables, not for collections. Most of the time you don't really want to have to give anyone the option to modify what you're passing them, you just want them to be able to iterate through it and to figure out what's contained in it. A corollary of this, which may not be present in all languages, which is why I just have it as an offshoot, is that use the functional facilities for result generation where they are available. So if you need just a subset of a list, use where to return that subset. If you need to return some values pre-calculated from a list, use select or map on a functional language. This is not going to return a new collection even, so it's not necessarily going to be it's not going to be using a significant amount more memory, unless you want to convert it into a collection. What it will be returned is something that is an enumerable that you can iterate through to access the new values, and which anybody that you give this to won't be able to change. And the fourth one is just use immutable collections. Now, this would be a bit of a pain if you had to implement it yourself, but luckily, at least for .NET and Java, there are some very good implementations already which do not act in place. Instead, when you do an add to a list, what it does is return a new instance of a list which contains this method, this new object embedded. Same with remove. Same with everything else. On the previous example that I showed you of the Fisher-Yates randomizer, if we had passed it an immutable collection, then we wouldn't need to worry about how long this object is living or how long this object is going to hold its data. We would know for a fact that that object would continue returning results that are consistent with the initial state. And we're not invalidating any pre-calculated information that it may be holding for performance reasons. Or of course, you can use a pretty nice and compact programming language like Clojure, which I would be more than happy to advocate if you want to go that route. Now, where to do this? First of all, the business logic. This one should be pretty much a no-brainer. Whether you have a monolith or a bunch of microservices or little green men reading packets and sending information back, you're going to have a big layer where your information, where the logic of your information handling lives. By definition, logic is about reasoning according to strict principles of validity. And nothing is less strict than not being able to know in which state your data is going to be about, even about any point in time. Logic is not about keeping track of a whole bunch of independent but subtly interrelated states that somebody may change. So make your business logic handle immutable data. That's going to be a significant win on the comprehensibility of your code base. Then there's the UI. Who was mentioned? You were mentioning earlier that UI might not be a good situation because UI would seem to be about manipulating and encapsulating state. Who would agree with that statement? Yeah, there's more. Now, what I would say actually is that the UI is about representing and helping manipulate state. Now, you're going to say potato maybe, but the UI, what it should be helping is helping the user figure out in which state is the application, which functions do I need to apply to it. For instance, somebody clicked on a button, so we need to apply the relevant function for that, and how to move it to the next state. If you have your entire application state, your UI represented as immutable data, then basically the current representation of the user interface is nothing but the last iteration of the functions that you apply to the data and that you use to build it. This is, for instance, the approach that Reframe, which is a Clojure library, a Clojure script library, takes with what it calls the event conveyor belt. It has a single place where it holds state. Any point in the application can raise events. The events are processed in a single channel. And every event application generates a new application state, which generates a new user interface, and which may trigger more events. I really recommend reading the Reframe README, even if you're not planning to work in Clojure, just because it will really help you think in a different way about user interfaces. This also has a gigantic advantage, which is that if there's one thing that I've had trouble figuring out historically, is how to debug user interfaces. And on something like Reframe, that becomes trivial. Because since the UI is pretty much the result of all the messages applied, if we just keep a log of the messages on the initial state, then we can immediately see why the UI ended up in what we consider an invalid state. And of course, we can be thinking, well, that's all fine for web applications. If we have two divs and a list box, then sure, you can do this thing. But actually, immutable data will make things better for more complex user interfaces. A great example is this talk from King.com, the company that makes Candy Crush and other games, about their default game engine. They used to have a user interface based on Eclipse, a completely mutable user interface, event-driven, the whole thing. And that was a complete mess for them to maintain and extend precisely because of the complexity of the user interface. What they ended up doing was moving to an immutable approach based on Clojure, where every bit in the user interface, even the shader used to draw this little HOTS thing, acts as a node on a directed acyclical graph. And every node can have multiple inputs, a single output, which may connect to other nodes, and it may contain complex computation inside it. And in the end, the user interface is basically just the result of a user interface rendering component probing the graph about its current state and sending them some events to change it to the next one. On the talk, they go over how difficult things were for them, how they simplified their lives, and how it made the editor a lot easier to both extend and reason about and completely remove the state box. So it turns out that it's actually the other way around. For a simple UI, when you're dealing with two divs and a list box, anything would do. But for a relatively complex user interface, immutability actually helps. Then there's your data layer. And I imagine that by this point you're looking at me funny. The data, that kinda sorta needs to change over time, right? Well, suppose that you're dealing with a system for financial transactions. Very simple case. You just need to record deposits and withdrawals. So when a deposit comes in, it's not immediately approved, right? The deposit starts spending and then it moves through the flow. What do? Do we just keep a transaction record with a single status column that we overwrite over time? I surely hope not. What I did, and this was way before I actually got into functional programming, was that you separated both concepts. You have the transaction, which was, say, a withdrawal for $10 created on a certain date, and then we kept the states for the transaction as separate records with a timestamp. The transaction with its current state was just a materialized view built out of the data, which is effectively the deltas that we have applied to the transaction over time with the reasons. This helped significantly with accountability, with seeing why something was in the state that it was. And if you have ever done something like this, you're already basically effectively thinking about along immutable lines for your data store. Now, we're going to step on the gas a bit here since we're running on time, but we're not to do this. And I found that this is more of a question of environment and constraint than a question of domain. So, for instance, is RAM a concern? Are you working on an Android, or somebody else mentioned an Arduino earlier? Well, then this is going to have a cost. Is the garbage hit a concern? Because this is undeniably going to have a garbage collection hit. Is raw performance a concern? Are you making a game where you're altering a whole bunch of properties 30 times per second? In any of these cases, you're going to need to do it judiciously. It's just up to you to determine exactly what judicious means. And finally, why do this? Well, everything we do in the development process is about trade-offs. And in this case, we're trading off a garbage collection hit for a code base that will be significantly easier to reason about. Remember what I said, that code base is read more than it is written. And a code base that is easier to reason about every time somebody has to read it will continue to pay off. The second one is that you will never have to wonder about side effects ever again when refactoring. Because the only thing that matters is one question: am I using this result value right now? Which brings us to something that I had never thought about before, but we're going to be writing code that's easier to delete. This is going to make significantly simple that to trim down our code bases over time, because code that cannot be causing any side effects, we be sure exactly the moment we can remove it. You're going to have easier threading because you're not going to need any locks. But more importantly, it's going to be easier to offload processing to a completely different machine even, because you know that even if you wrote this as a monolith, there's no part of your system that is going to be relying on any computational side effects. So you can just move it to a different box if you find that this is way too heavy for your single machine. You're never going to need to ask this question again of who's holding these objects. Who cares? Nothing that you can do is going to affect them. And the main thing is that immutability is going to let you focus on comprehension of what's going on, not on memory of what's going on inside this call. This is an argument that I keep making, and I'm sure it's not a very popular one because it's not a very alpha programmer kind of argument, but we have a faulty brain. Our brains suck, quite frankly. We forget things, we make assumptions, we get distracted. The more balls we have to juggle, the higher the chances that we're going to drop one. So the fewer assumptions our brains have to make about the code base, the fewer aspects that your brain has to remember about what's going on inside it, the better you're going to be, because the least errors that you're going to make. So, in conclusion, as I hope we saw, immutability frees you to change your mind about implementation details, about even where processing is taking place. If something can mutate, somebody will mutate it. Worse, further down the road, somebody else is going to rely on that mutation, at which point you're stuck with it. And you have lost control, the control that you need to make decisions. Because to be in control, you have to know. You have to be certain about what's going on in the code base. And mutability demands that you take things on faith. And remember that faith is at odds with knowing. So, if you get a chance, try some functional patterns, particularly if you have been working on object-oriented programming for a while. And you'll see that this will help you replace trust in your code base with actual certainty about what's happening. Now, Any question? I think we have like 30 seconds. Yes.
I have a question. I know there was a lot of concern in the direction of instantiating new objects out of already existing objects, like for strings, for instance,
Yes.
for performance reasons. Because I know, for instance, in C# string builder sometimes is used instead of having strings and doing concatenations on them for the performance goal.
Yes, that is.
In this direction.
Well, that's actually why I mentioned that if we're making trade-offs here. So definitely, in some cases, we are going to be aware of those things.
And what should we do then? Should we try to isolate the immutability somehow from the mutable parts?
Indeed, in
Strategies?
the approach that is followed in Clojure is that it is considered that local mutability is fine. So if you have something that needs to build a value that would be discarding a lot of intermediate steps, it's fine if you do this in a immutable manner, as long as you return an immutable value. Because the unit of thought here is the function. If nothing immutable is ever escaping the function, if nothing immutable has any side effect ever, then you're fine. It's a similar approach up to a point to a string builder, where you could remove any of the elements in the string builder before you generate the final immutable string.
Okay, thank you.
Just in addition to that, the immutable collections framework can be highly optimized for that, because they just reference the old things if you add or remove things and keep state in there. And so.
Oh, yes, actually there's a few very good articles on the implementation of persistent vectors in Clojure, which might be a good read for that. So, sorry, you.
In a VDD approach, you have data values, okay, that are immutable, and you have entities which are by definition mutable. How do you deal with this kind of thing?
Well, I would need to look specifically at the case. If you mean by entities, the stuff like, let's say, it's coming from the database, or, well, in that case, you're dealing with immutable data when you're doing your processing, and of course, you're going to have that mutability point when you do save things. So, at that point, you just need to apply whatever business rules are appropriate. Yes.
If you have a system where the previous state doesn't matter, you care only about the current state. That's the specific of your project. And what would be the most benefit of immutability?
If you don't care about the previous state at all, if you don't have a shared state, like for instance, nobody else is holding your collection, if this is something like you only care about the state of the video buffer right now, then it's a case where it doesn't apply. Because you don't really care, you don't have any shared state, but I've found that to be very rarely the case in my own experience. Like I said, it's mostly about when you're doing real-time stuff with data that I have right now and nothing else. It's the system equivalent of a goldfish. So. Anything else? Okay, then I'm going to stop delaying.
A PowerPoint presentation somewhere.
Yeah, I'll be happy to upload the slides, and just grab my Twitter account and I'll post the link in there. I haven't uploaded them, so thanks for the time. And I was told to remind everybody to give feedback. I think it's on the door, so I have done my duty. Thank you.